participants. Good morning to everybody. So basically, as Charu has already introduced me, so basically I am a former scientist in the Space Application Center, and today's my topic is what is the basic infrastructure for meteorological satellites and what are the data products from that. So with that, without going much into those background, let me come directly into the point. So basically, the purpose of all the meteorological satellites is basically operational. So it is operational means basically to first to understand the weather, and ultimate objective is to predict the weather. And that is somewhere or somehow all the weather satellites or all the meteorological satellites have a common purpose to improve the weather prediction. And that is the very fundamental to that. In today's time, a lot of data from these satellites go to the weather models and weather prediction directly or indirectly. So basically, you should know that what is the advantage and what is the what are the benefits of the weather forecasting. Nowadays, today's time, lots of industries depend upon the weather forecasting. For example, even a sport event heavily dependent upon whether what kind of weather you can expect on those days, because these bookings are made much in advance, and then suddenly this match gets cancelled out, and then all these things. So these advanced understanding of what kind of weather will be there. Everybody will want that kind of information, and it has a lot of commercial benefits. Apart from that, there are other sectors. For example, the first and foremost is agriculture, because in this agriculture, the timing of the rainfall and the timing of the heat waves and timing of when it will not rain, even the wind speed, it depends. It affects a lot on the agriculture yield. For example, how the wind speed can affect when they are applying the fertilizer on this. Spray. So if the winds are not favorable, then this whatever you are flowing this in insecticides from the drones or from the ground-based instruments, it has an inverse effect. Actually, the winds blows everything out, and then you don't get the desired benefits. So even a parameter such as wind speed can have a lot of impact on the agriculture and agriculture production, productivity, and its benefits, etc. Rainfall, heat, temperature, etc. Users of the weather services is basically the aviation sector. Aviation, whenever the airplane leaves airport, it leaves airport with somewhat reserve fuel in that. It is not that it is just from A point to B point. For example, some plane is leaving from Delhi and it has to go to Bangalore. It is not just sufficient fuel. It takes some extra fuel, because in case there is some bad weather, then they can manage to fly in the air for some time and wait for their chance to park. But if there is a bad weather for a very long time, then this becomes a very emergency situation. Also the turbulence, whatever is the turbulence on the way, it affects the movement of the aircrafts, and it makes a lot of difference on their fuel consumption, particularly during the international flights. They take the routes where there are high jet streams are there, or where there are high winds are blowing. So they take that path, which is more fuel economic for them. So this is one sector which takes a lot of advantage of the weather forecasting services. For example, commercials, commodities, like the ocean activities. This is a very big sector, actually. You know that there are a lot of platforms, like the oil rig platforms in the offshore platforms are there. From the offshore platforms, it gets affected not even by the rain or the winds. It's affected by the lot of storm surge and the wave heights. If there are a lot of wave heights, then it affects the productivity, and not only it affects the productivity for those days, it affects the productivity for the next many weeks, because once that platform is vacated, then it takes very long time to resume the work at that point. So there are a lot of other things like tropical cyclones. These are the disaster management, horticulture, agriculture, commercial, tourism industries. The sports industry, they wait a lot for the snowfall season. Whenever there is a snowfall, and those exact dates of when there are likely to be snow. Whether sometimes this whole season there is no snowfall. So those kind of things also affect the tourism and other sectors. So there are actually, and these are very limited cases. There are n number of other application and the what is that called, the use cases in which the weather forecasting is important. And these are the areas where the satellite weather forecasting, satellite-based weather predictions are important. In which it means the weather prediction services where directly satellite data is used without much going into the model. So these are the satellite predictions which are done, for example, for the nowcasting, for a lot of other predictions, tropical cyclone monitoring, crop forecasting. ISRO launches, I have worked in ISRO, and recently we have launched a Chandrayaan 3 satellite, Chandrayaan 3 rocket into that whole mission was going to go to the Chandrayaan mission. And actually I participated before that into this Mangalyaan, Chandrayaan 1, Chandrayaan 2, these missions, and these are very, very important to predict certain weather parameters. For example, the lightning, occurrence of lightning, wind speed, the thunderstorm, convective weather, and wind profiles, how the wind will vary along the way into the when the rocket is within first 8 kilometers into the atmosphere. Then the wind, very high winds can, it can tilt the rocket's path, and then it is very important to predict those winds. They are very, very important parameters. Another thing is the convectiveness, lightning intensity, etc. Then air quality. Air quality is one parameter which is basically measured directly from the satellites. Solar power, wind energy, street heat maps. For example, these kind of street scale heat waves. Within one city, when there is a heat wave, these heat parameters or heat intensity is not spread uniformly across the entire city. Some part of the city which are having more infrastructure and more buildings and more road network, railway, etc., the impact of heat is more on those locations, and the people living in those areas are more affected by the heat. So even though on a city the temperature is on average, for example, 5 degrees above climatology, but in some areas it can be even 10 degrees above climatology. So this affects directly the human health in living in those areas, and they become very vulnerable to that. So these kind of things, can be determined directly based upon satellite observation. What is the structure of those heat waves, and what are the structure of those heat stress that is acting on the in different parts of a locality? And this is the similar kind of things. This is a very highly localized map of the temperature and even the rainfall. So this is these kind of things where the satellite gives you direct information, and they can be used for certain amount of weather forecasting. And as you know that, as you might have seen that nowadays with the climate change, the risk of hydrometeorological hazards is increasing day by day. Hydrometeorological hazards means which are directly related to meteorology, directly related to the weather. For example, floods. Nowadays, you can see that so many floods have occurred, and you might have seen those pictures in Himachal Pradesh or Uttarakhand. The very high amount of rainfall, and this kind of risks and this kind of cost of this kind of hydrometeorological hazards is enormous. And day after day, they are actually increasing, and their intensities are increasing. There is a record of that. Actually, this is a published record of that. And how do you know all those things, whether they are increasing or they are not increasing? Because rain gauges are not everywhere, so we have to have a record which can provide us information that whether they are increasing or not. Tropical cyclones. There is a certain concern about this, because tropical cyclones, whether they will come, how much they will come, what will happen to their frequency, what will happen to their intensity. Bonds, and they have very high amount of economic activities that are going on there. So even one tropical cyclone, if it hits at a wrong place, it can this Mumbai is considered the capital of economic capital of India. So if there's a trend that the cyclones are hitting more towards the western part, so it is, this is a matter of some concern, because then the people who are making some infrastructure there, they will consider these facts that the tropical cyclone can hit, and what kind of strong infrastructure they should build on there, or they should build a infrastructure there at all or not. So this kind of what is the risk and what are the benefit, kind of cost benefit analysis can be done if you know the understanding of the tropical cyclone. This can be done only from satellites, that what is the intensity, what is the occurrence, what is frequency, etc. And droughts are also, drought is very unnoticed disaster. People do not notice it, because it happens very slowly. It does not rain for 1 day, 2 day, 3 week, 4 week, for 4 months, 3 months, and next year it does not rain. People, because it occurs very silently and slow, very silently. The ground loses its productivity and its capacity to carry out agricultural activity over there. And the repercussions of those droughts is quite long and quite vast. And when there's a drought occurs, it doesn't occur over a small area. It occurs over a very vast area, and it affects, I think, millions of people. So that is why these all things are, this is the cost of this. This I have shown you in this this graph. And heat wave is actually becoming now a big problem, because year after year, even in this year, even in the month of March or February, there was occurrences of heat waves, and just in the month of March. So these heat waves are also becoming more severe and more widespread, more common, more frequent. So all these things, for monitoring all those things, we require a lot of satellite observations from multiple sensors and multiple years, so that we can have a clear idea that what is happening to these events. For example, these tropical cyclones, tropical cyclones, you can see this is a picture of 2019. The record-breaking eight cyclones occurred over there. This year also, there is a big cyclone occurred in the coast of Gujarat, and these trends are quite becoming more and more common nowadays, and they are becoming more and more severe. So this is putting the entire safety of the coastal area into risk. So in the current situation, there is only one sensor only one method which operationally provides every half an hour, which provides the intensity of tropical cyclone. There is no instrument which can survive the tropical cyclone. They cannot provide the entire range of the tropical cyclone intensity. So there are some indirect methods which are developed in 1975, 1974. You can see 40, 50 years back, and still they are being used, and they are becoming they are being used very valuably, and these records are maintained very, very carefully, so that we can know what is happening to the tropical cyclone intensity worldwide. Not only here, tropical cyclones are everywhere. They are in Japan, they are in America, they are in South America, Australia, South Indian Oceans. So this is the trend. Generally, people are thinking that there is a general consensus that the high intensity tropical cyclones are becoming more intense, more frequent, and the low intensity tropical cyclones are becoming slightly less frequent. And this is the trend. Then extreme years, extreme rainfall, as you all know that these, you can see this blue are increasing every year. So even in the years when rainfall is not so much, even meteorologically they are not very high rainfall years, but still, for example, this year there was a huge amount of heavy floods, and we have all seen those kind of pictures. But the rainfall till now is not very high. If you see the average of India, it is just 0% above normal. So it is just as much as it should have happened. But the distribution of rainfall has changed. Now the rainfall is occurring more in terms of the heavy events. Not that the rain is occurring every day, slowly, slightly. When it rains very heavily. Otherwise, it does not rain for many days. So the distribution is changing. It is going toward the high intensity side. So that is this is very important to understand what is the mechanism and why. What is the reason for those things? So all these things, they start with observation. So every process for prediction or even understanding, it starts with observation. First, we observe that what is the nature of certain things, what is the behavior, whether our observations are correct or not, whether this is the right method to observe or not. Then after observation, we go to the second stage to understand those processes, why it is happening. We are observing that, okay, the rainfall is increasing, rainfall, high intensity rainfall cases are increasing. But the question then comes that what is the mechanism? Then we try to apply our physics, we make model to understand or to explain this behavior of the rainfall. So this is how this understanding, and then once we have gained understanding, we have made a algorithm for understanding, explaining that process. Then we can use that the same thing for prediction of the thing. So that is how all the weather models, all very complex models, they have been developed over the period of many years. I think over a period of approximately 60 years. People have been observing this. Earlier, the satellites were not so much. Satellites are relatively new, but people are making ground measurements, taking a lot of instruments, they are taking heavy instrument to the ground. So this all rainfall parameterization, all the physics parameterization, cloud formation, how the cloud forms, how the evaporation takes place, how the solar radiation interacts with our atmosphere. All those things are made into the highly theoretical framework, and then they have been put into the models, and that is how the models are becoming more and more accurate year after year. But we require observation not only to understand but also to verify. Then once we predict something, then how do we know that the prediction is correct or not? So again, we need the observation for that. So there is one more term to do that. Again, goes back to the observation to verify that whatever we are thinking is correct, or where our theory is failing. So we predict that there will be a lot of cloudiness under these circumstances, but it is not happening. Then why it is not happening? In which places it is not happening? Then we apply some other processes into that, we include other processes, and then we try to make our models more and more perfect. So initially, as I was mentioning, that the conventional observation were made at the surface, and there were basically the measurements of wind, temperature, humidity, radiation, etc. Still, these observations are extremely valuable. Some places it is more valuable than satellite observations. So, for example, they are very near to the ground, and very near to the ground, these conditions are extremely important for a lot of applications like agriculture, hydrology, and many other applications. Most importantly, agriculture. So agriculture is, as you know, that it is happening at the ground. So the ground conditions are very important. What is the humidity? What is the soil moisture, soil temperature, radiation, etc. All these things. Satellites are still not very good getting the values very near to the ground. So these instruments, even after the development of satellites, these instruments are still very valuable. And so what they measure. So these are basically the traditional way it is doing. So they measure wind, temperature, pressure, humidity, rainfall, solar radiation, etc. And there are approximately 10,000 sites which maintain these observations, and these 10,000 sites are basically the government sites. So these are maintained by different governments, like Government of India, Government of Australia, Africa, America, USA, etc. These are somewhere they are maintained by the government agencies, Apart from that, there are 10,000 government, and there are 250,000 plus. They are maintained by private people. So everybody who has a big farm or who has some interest in agriculture or any research university or research organization, research institute, research center, all these people maintain this kind of observations. You can see that there is a big density of these observations in the United States. These are the private weather stations, and they are in the Europe and Japan and in some part of Australia, South Africa, some part of the South America. There is a big density, and they are approximately 25 times more than the number of stations maintained by the government. Now let me tell you what is the problem with these observations. The main problem with these observations is that all these 2,500 instruments which are put by different people, they don't measure the same thing. There are some biases between them, and they never know that what are the biases. For example, I have one instrument in my house, and somebody else has some instrument in the park. So we don't know whether they are calibrated with respect to each other or not. For example, it is like a watch. So every instrument is like a watch. So I know my watch is, according to my watch, there is a 1155. In somebody's watch, it may be 1156 or so 57. So even though both watches are very expensive, but there is slight difference between these two measurements. And it is very difficult to know because I cannot contact everybody. All these people who have maintained these instruments, they don't go to other people and then they ask, okay, let me calibrate our instrument together. And even the instrument from the same company can give very different readings. So that is the problem. That is called the lack of representativeness. They are not representative. They are very accurate, but unless they are calibrated to the same one standard, for example, in the watch we have a standard. We have in my watch is actually calibrated with respect to the internet. Okay, your watch is also calibrated with respect to internet. So that is why my watch and your watch is giving same measurement. But this is not the case with these instruments. So that is why sometimes they give very, very widely different observations. And if you try to put those observations into some common model, they create some problem of biases. And this is why even though they are very huge in number, they are mostly confined to a personal applications only. So this is one thing where the satellite have one advantage. Similarly, the atmosphere is not confined to the surface. So an atmosphere has a vertical structure, and vertical structure goes up to 8 to 10 kilometers, where you have a lot of winds are blowing up, a lot of clouds are being transported, water vapor is being transported at different vertical levels. So it is not only at the surface that things are moving or things are taking place or events are happening. The weather that you can feel tomorrow, it is affected by the entire vertical three-dimensional structure of the atmosphere. So it is not just so. When you try to predict the weather for maybe 2 days or 3 days in advance, surface measurements are not sufficient for that. So you have to resolve the complete structure of the atmosphere. So for that, people have realized it for long back, and the instrument that is used for that is the weather balloon. So weather balloon nowadays, it is attached with some GPS instrument as well as a very high quality humidity and temperature sensor. Now the quality of these humidity and temperature sensors are extremely high, and they are very, very accurate. And the GPS actually gives you very accurate positioning of the balloon. So it can be used to derive the winds also, because at 1 minute before the balloon is at this place, 1 minute after balloon is at that place. So between these two, I can calculate the wind by which wind speed the balloon is blowing. So it can give you the temperature, humidity, and winds, and pressure also. So this is very valuable, but this is very expensive. It is very, very, very expensive to maintain this kind of instrument, and it requires a big expertise to operate this kind of system, because most of these balloons are filled with the hydrogen, and this hydrogen is actually manufactured there itself. They don't carry hydrogen. Helium is, you can put helium. Hydrogen is very, very dangerous gas. You know, this hydrogen, there is it if it goes out of control, it explodes actually. If there is a, so you require very experienced people to handle this kind of facility. So I have worked in the Sriharikota, so I know that in Sriharikota launching site, these kind of balloons were launched, and how much time it takes and how much effort it takes. It takes 3 to 4 people to launch one balloon, and you have to go there at 5 o'clock in the morning and fill with the hydrogen. And if there is small mistake, you know, it can blast. And when hydrogen burns, you know, it burns without any flame. It is invisible flame actually. So it is more dangerous. So and not only that, it is expensive also. You have to have those kind of high quality balloons, rupture proof balloons, which do not rupture with the small pressure. So because of that, there are very few instruments there. For example, there are only 1,000 stations which operate these weather balloons approximately twice a day. Most people do it once a day, but twice a day, I think some agencies do twice a day. Some agencies do even 4 times a day. But as I told you, that to operating and maintaining this kind of facility is completely manual, and it's not so easy. So that is why worldwide there are only 1,000 observations, and there is no observation over the ocean, like in the middle of the Atlantic, middle of the Pacific. There is nothing. Even on the desert, you know, desert regions like the Mongolia desert, in the Thar desert, there are no facilities. In the high snow areas like Greenland and Alaska and Siberia, etc., these facilities are not there. So that is why, you know, we require some mechanism by which we can get the observations at all the places, and there is one single instrument that is providing the observation. So that is okay. One more observation I'll tell you. This is coming from the upper air, coming from the aircrafts. When the aircraft takes off from the runway and slowly gains height, you know, at every second it is measuring the temperature and humidity. There is a very, very valuable data. It is actually the ground truth, real data where the aircraft is passing. So it provides temperature, humidity, winds, and pressure data as it takes off and gains a height of approximately 10 kilometers. So it constantly gets the data. So you can see that this is the amount of data from those aircraft during the. So when there was a lockdown and the flights were not there, there is a big shortage of this data, and this is, you know, extremely valuable source of information, and it has a very big impact on the weather forecasting. You know, this is very valuable data for weather prediction, because this is it is actually, you know, the aircraft is actually touching that wind from which it is taking the measurements. So this is very valuable. This is not a remote observation. It is actually in situ observation. So this is one observation. Apart from that, there are ocean in situ observation like Argos satellite, Argos system. So you can see that there is not only on the Earth but over the ocean, deep ocean surfaces. What is happening inside the deep layers of the ocean? There are a number of other instruments are put, which are the buoys and the thermographs and the Argos, etc. So there is a need for an observation platform that can cover weather and climate adequately, which has the scale, coverage, etc. So we have to cover the entire Earth. Second thing, we have to cover. Well, I'll come briefly. There are satellite. This is basically the satellite. So in today's time, there is no need to tell that what is the satellite and what is so important of the satellite. But I'll tell you what are the advantages of satellite observations. So satellites, meteorological satellites, mostly operate from 2 orbits. One is called the geostationary, one is called the polar. Polar actually rotates from one pole to another pole, not precisely, but at some angle also. It's not from 90 degree to 90 degree. Sometimes it's 80 degree to 80 degree also. Even from 35 degree to 35 degree. It's not a big deal, but it is a low Earth orbiting satellite or the polar satellite. But whatever is moving with Earth at the same constant speed, rotational speed as the Earth, that is called the geostationary, and this is the polar or the low Earth orbiting satellites. So what is the advantage of satellite observation? Number one, coverage. It gives you the global coverage. So there is no other instrument that can give you the global coverage. It is very difficult to take the same instrument to all the places and take the measurement of the globe. That's very difficult. Second thing is the repeatability. That these observations are repeated. For example, from geostationary, nowadays geostationary satellites are taking measurements at every 10 minutes or every 15 minutes. You know, this technology has come. Technology has changed. The imaging technology has changed. Like in mobile, you know, in your mobile, you can take within a fraction of a second, you can click a picture. The same kind of technology, even the satellite sensors are now assuming they are taking the whole frame and then capturing the whole frame at once. Earlier, they were capturing line by line, one line by line. So it was taking huge amount of time. For example, in the previous generation of InSat satellites, it was taking 30 minutes time to cover from this part of the Earth to this. So they cover line by line. They cover one line, two line, three line, four line. Nowadays, new sensors, they capture the entire thing at once. And then their accuracy and their resolution, spectral resolution, etc., is very high. Second thing, repeatability is very big advantage that you can take the repeated observations. And the last thing and very important thing is the representativeness. It is very important quality of satellite observation. What is representative means? It is the same instrument. Suppose you are taking the measurements from one satellite. It is the same instrument which is taking measurements for over the Europe also, is taking measurement for the India also, is taking measurement for the ocean also, for the mountain, everywhere it is the same instrument. So it means if there is an error in this instrument or a bias in this instrument, you have to apply this bias only once. You have to correct the biases only once, and then the whole observation can be corrected. So as I gave you the example of the last ground-based instrument, that they are not calibrated against each other. It is much easier to calibrate a satellite observation compared to because it is global. It is the same observation. It is the same instrument which is taking the observation throughout the world, or throughout at least one hemisphere of the world. For example, geostationary always looks at one third of the globe. It observes approximately 1/3 of the globe. So that 1/3, it is measured by the same instrument. So sometimes, you know, this calibration of satellite observations is the big topic, and it is taken very seriously. There are international meetings for that. There are international teams are built up for that, which calibrate satellites against each other or against one polar orbiting satellite. It is extremely important, because if you don't calibrate your satellites, you know, then you can have improper conclusions. For example, your satellite is giving a very high temperature at some place, which might not be correct because it is biased observation. You may conclude that, okay, yeah, it is very high heat wave and temperature of India is rising at a very high rate, which is not correct because your instruments is not correct. So it has to be calibrated. So that is why the calibration is extremely important. And there is a team with a global effort that is called the G6, the Global Satellite Intercomparison Project. So so basically, it is global intercalibration of satellites is a very big effort, which all the nations which are operating satellites, they participate in that. This is an annual meeting, sometimes in different parts of the world. It happens every year, and that is why these things are calibrated. So these satellites, you know, how they started? They started approximately 63 years ago, when there was a first weather satellite was launched on a weather satellite was launched, which was basically a analog camera. It was not even a digital camera. So you can take only pictures, not the value of what is the cloud, the value, what is the brightest temperature, what is the actual value, what is the lat long, etc. You don't know. From that you get only and only pictures. That's all. In the, you know, in old times, you know, you are taking the black and white pictures, and it was no digital. You cannot compress it, you cannot resize it, you cannot do it. It was only an analog signal which was transformed into picture. It's a television infrared operational satellite. It's basically T is for television. It means it's basically exactly the same principle as television you was using at that time, producing an analog signal, but it gives a remarkable idea that to observe different weather systems, particularly the tropical cyclones, hurricanes. If there is a hurricane somewhere, then TIROS satellite can capture that, and then it can provide some enough warning. And then also the people realized, for example, this is the composite picture from TIROS. People realize that the weather is not confined to one country or one city, and then the weather at one point, one area can be affected by the phenomena which is happening at thousands of kilometers away. For example, what is happening at Africa right now? What is happening? What is happening in Africa? It can affect Indian monsoon after 15 days. So that is the thing people have realized, that these kind of waves are traveling, and they are traveling throughout the world, and they are not confined to a particular country. So this weather does not know the boundaries of the country. So it can, for example, the cyclone that comes to India, that might have been generated just in the Indo-China Sea. So they are generated at Indo-China Sea, and then they slowly migrate, gets more powerful at the Bay of Bengal, and they hit Indian coast. So these things are extremely teleconnected. The teleconnections are very large, and this kind of teleconnections, people got to know some idea of the teleconnection through the satellite pictures, and then they embarked upon utilizing these observations, making these observations more perfect, more meaningful, more useful for the models, more useful for the weather prediction. And then they developed the system, sensors, considering all those factors, whether it will be able to capture those kind of rainfall events, how much rainfall we want to capture, what will be the saturation level of those sensors. So this is the satellite development. Weather satellite development is a combined effort between the weather meteorological scientists and the engineers. So they sit together, and then they find out, okay, how much is the rainfall we are expecting, so what kind of rainfall we should make at one particular instantaneous time, how much rainfall we should expect to get, because every sensor gets saturated at some particular point of time or a particular point of value. For example, if the cloud brightness, so if the cloud is very bright, so initially the satellite measurements will be able to differentiate between different brightness of the clouds, but ultimately the cloud becomes so bright that satellites will not be able to differentiate. So after that, between 90% and 100%, the satellites have the same value. It does not differentiate between that. So we say that the sensor has saturated at that point. So this sensor saturation comes for many things, like winds also. When we are measuring the winds, for example, this is the development of the satellite sensors from 1960 onwards. So in 1960, this was just a camera. This was a television camera. This is basically a old. You might have seen old generation pictures, like black and white pictures. So it was like that only. Then in 1960-70, then people went to the digitization of this thing. So now you are getting the picture which are digital, which you can analyze, and we can make some pattern from that. You can analyze this data in a computer. We can read this as a matrix, and this is very important. Then slowly in 1970s and 80s, this was a golden period for the development of microwave satellites. The microwave sensors, there was a big thrust on microwave sensors in 1970s and 80s. There were big guys and big beautiful minds working on these reasons, and they focused more on the microwave. Microwave has a big advantage, that microwave can penetrate clouds, like visible and infrared. If there is a cloud layer, you don't know what is happening below that cloud layers. But the microwave are having a bigger wavelength, and that is why they are not affected by the presence of clouds. So if suppose for example you want to know the sea surface temperature, and if the cloud is completely covered with the sky is completely covered with the clouds, so the infrared and the visible sensors will not be able to know that what is happening below. But the microwave sensors can see the surface very easily. They are not affected by the clouds because they have a very big wavelength, and the cloud particle size is very small. So there is no effect of cloud particles. Even some microwave frequencies are there which are not affected even by rain, not even by heavy rain. So that is the beauty of microwave, and that is why people actually what you can say, they contributed a lot of their time and a lot of their energy into the development of microwave sensors. And after that, this you can see this picture shows you the surface winds, and this is one of the very valuable observations coming from microwave satellites. They can give you the winds over the ocean surface, not at the ground surface, but ocean surface, because when there is a wind is blowing over the ocean, they create a lot of waves, and they create a roughness into the sea, and this roughness is directly proportional to the winds that is blowing over the ocean. So from this roughness changes the emissivity. So from this roughness, they can get an idea that okay, this might be the amount of wind speed over there, and it is fairly accurate. Actually, it is accurate to less than 2 meter per second. So it's quite good accuracy from a satellite platform. Then we went to the microwave further development, and then people made the microwave rain radars. And microwave rain radars means you can not only see the rainfall at the surface, but you can see the complete structure of the rainfall. Vertically, how the rainfall is vertically distributed. How much rainfall is happening at the 5-kilometer height? What is the rainfall at 2-kilometer height? What is the rainfall at 9-kilometer height? So sometimes this information is very valuable. Why this information is valuable? Because sometimes when the tropical cyclones gets intensified, they create a convective towers. Big towers are created inside the tropical cyclones, and they are the indicators that the tropical cyclone is going to intensify. So this kind of information is obtained from this kind of rain radars, which can give you the 3-dimensional profiles of rain. Similarly, there was a concept of hyperspectral imager and sounders, but actually this hyperspectral means there was a sensor which used to sense the 3-dimensional structure of the water vapor. Not water, but water vapor. Water vapor is a gas. So from that, they have a special lines around the water vapor. And from this water vapor, by sensing the water vapor, they can find out what is the movement of water vapor. And through this, even not in a cloudy atmosphere, in a clear atmosphere, because it is a infrared based system. So in the clear atmosphere, they can find out what is the profile of the wind, how the wind is actually blowing at different heights, and it is very important. It is very important for weather forecasting, tropical cyclone development, etc. But actually, unfortunately, this project can never come out, and this estimate is still lying somewhere in some US university, but it was never flown on any of the satellites. But this was developed even in 2005, 2010, even 15-20 years before now. Anyway, this effort could not materialize, but just 2 or 3 years ago, there is one instrument came which is called the atmospheric wind profiler. So this atmospheric wind profiler, basically, it is a laser system. It's a very powerful laser, very powerful but safe for the human beings. So it is it works on infrared frequencies, and it basically, it senses. It is a Doppler laser, and it senses the movement of the aerosols in the lower atmosphere and movement of the molecules in the upper atmosphere. Because in the upper atmosphere there are very few aerosols. So by the tracking of the aerosols, it can find out what are their wind speed. So this is a very important and very unique kind of observation, where you not only get the wind speed at the surface, but you get the wind speed at 1 kilometer interval. At surface, 1 kilometer, 2 kilometer, 3, 4, 5, 6, 7, 8 kilometers, like that. It's very unique kind of measurement, and very power consuming instrument. It requires a lot of power. So that is why the mission life is less, and it does not take continuous measurements. Actually, it becomes off. After taking measurements for maybe 10 seconds, it becomes off for 20 seconds. Just so that the mission life can be improved, because these kind of laser active instruments, laser based active microwave radar based instruments, they consume a lot of power, and they entirely worked upon a onboard battery system. so which has a limited life. So that is why these instruments, particularly the active I'll tell you what are those instruments. So this is just a glimpse of how the meteorological satellite sensing techniques have developed over a period of time. Anyway, this is the most basic satellite orbit, that is called the geostationary satellite. The geostationary, as the name applies, name implies that it is stationary with respect to the Earth. So it means relatively, its relative motion, angular motion, is same as the Earth, and that is achieved at 36,000 kilometer height above equator. So at any other latitude, it is not possible to have this kind of orbit. But essentially, it has to be near the equator, and exactly at 36,000 kilometer height. So there you can get exactly same angular velocity as is required to make the Earth look stationary. But there is many advantages of this system, because we need to know the motion of the clouds, motion of the hurricanes, motion of the tropical cyclones, waves, etc., irrespective of the Earth motion. So if Earth is moving, clouds are moving, then it is difficult, and satellite is also moving, then it becomes a complex problem to register those kind of motions. So particularly to track operationally, so this geostationary is a requirement of all the tropical countries or near the tropical countries which are living near the tropics. It is essential. Without that, their meteorological services cannot operate. It is extremely important to monitor the weather on time-to-time basis. So this is a very essential element of all weather satellites. So geostationary satellites are in the polar orbiting. So now, actually, practically it can cover the entire Earth. Means entire Earth means the one part of the Earth. Actually, practically it is 1/3 of the Earth or 1/4. So what is happening that only about plus minus 50 degree it is useful. Plus minus 50 degree from the equator it is useful, because beyond that, the distortion becomes so large that even one pixel, you can many clouds, many kilometers of the clouds come, and then it becomes at a very slant angle, which is not very favorable for making a good useful measurements of the Earth. It is not practical. So we use only plus minus 50, even plus minus even less than that, for practical purpose. So we can derive the winds and all these things, cloud information, cloud aerosols, fog, heat, etc., temperature, everything we can derive properly within plus minus 50 degree from equator. So that is one big limitation of these things. So the countries which are beyond 50 degree, like Russia, Ukraine, and other parts of the Europe, and the many parts of America, etc., Australia, etc., how they get benefited from these satellites. So they have a very different kind of other approach, because they are not benefited much by these satellites. Of course, Australia has a big part in the tropics, so this kind of there is some part of Australia, but even southern part or extreme northern part of northern countries, they don't have much advantage from geostationary satellites. So they have a different technique. First of all, they can go to the polar satellites. Polar satellite can cover the upper latitudes very well, but the problem is that the polar satellites have a repeativity which is not very satisfactory. For example, if a polar satellite comes to some place, it will come to the same place after maybe 6, 7, 8 to 12 hours. Or in the tropics, it will come to the same location after 12 hours, and at the extreme north and south, it can come. So from here, it will come every 1 hour, every 1.5 hour approximately. So this is again one limitation, because nobody would like to wait for 1.5 hour to take one measurement. 1.5 hour is too long time. It's approximately 98 minutes, which is more than 1.5 hour actually. It's approximately 100 minutes. So either you should have many of such satellites which can go one after the other, and you can get a good decent coverage. Second thing, coverage is also one problem. So that is one more solution to this problem is the geosynchronous orbit. You know what is geosynchronous? Geosynchronous also has the time period of 24 hours, but it is not geostationary. It is geosynchronous. So there is a difference between geosynchronous and geostationary. Geosynchronous has this kind of orbit, you know, so it can be placed at any angle. So it is not necessarily has to be at the equator. It can have any angle. So they put in such a way that it has a small small. It is a highly elliptical orbit, and one side it is very near to the Earth, and other side it is very far from the Earth. So this kind of arrangement, you know what it does? According to Kepler's law, this satellite, when it comes to this part of the globe, it passes this region very quickly. So this is the Kepler's very famous law of the orbital dynamics, that the orbit sweeps the same area in the same time, and when it goes here, then it remains in this position for a very long time. So it moves here very slow. So basically, suppose this satellite is by Russia, for example. Russia has this kind of satellites. When it is here, you know, it keeps on watching at Russia for a very long time, and it goes here slowly, it moves here, and very quickly it comes back again. So this is the arrangement of a geosynchronous orbit, and this is the orbital coverage of the geosynchronous. It makes a figure of 8 kind of things, you know. This is roughly, you know, it makes a, if you take the orbital projection on the ground, it makes a 8, number 8 kind of figure. And that is why, you know, it is very fast. It passes this region very fast, and the other side it is very slow. You can see the motion here. So it becomes it slows down here very much, and then it passes this place very quickly. So that is why this kind of orbits are favorable. So these are called geosynchronous satellite orbits. Now, how satellites take observations? Now, this one important question is that what satellite measures, first of all. For example, we can use satellites for measuring winds, temperature, radiation, aerosols, etc. But satellite does not measure temperature, or satellite does not measure winds. Satellite measures only one thing. Satellite measures the radiances, or the reflectances, or the reflected radiance. It measures only radiation, nothing else. And you have to make a algorithm which can convert these radiations into the meaningful quantities. So basically the satellites, hello. Yeah. So satellites measure, hello. Is there any problem with the sound?
No, sir. You are audible. You may continue.
Okay. So you can see that there is a very big range of the electromagnetic radiation. It starts from short wave, gamma rays, from X-rays, ultraviolet, visible, infrared, microwave, radio waves, and very long waves also. But satellites, you know, for meteorological purpose, satellites work in mostly from visible, infrared, and the microwave, these frequencies, and to some extent in the radio waves, which I'll tell you how these radio waves are being used in the meteorological sensors. But we don't go much into these frequencies because so far whatever meteorological parameters we want to get, we can get from these frequencies only. So we use a very limited part of the ultraviolet of the electromagnetic spectrum, and these serve our purpose so far very nicely. Now there are two kinds of sensors in the satellite. One is called the active sensor, and one is called the passive. Actually, passive comes first. The passive sensors means basically which does not use its own source of illumination, like our eyes. Our eyes is kind of a passive sensors because our eyes cannot work when there is dark. So if there is no other source of illumination, our eyes cannot produce the light itself. Our eyes only pick up whatever is reflected from the solar radiation, or from the inside my room, whatever is the light, whatever is the bulb is reflecting, or whatever my computer is emitting the radiation, I'm able to see that. But if everything is switched off, my eyes will be of no use. So our human eyes are basically kind of a passive sensor. So passive sensor means we are using some source like the emission from the earth. Earth not only reflects the sunlight, but it emits the radiation in the night time also, or in the daytime also, in the form of thermal infrared radiation. So this emitted radiation or reflected radiation, whatever we are using, it is basically passive sensing. Passive sensing has an advantage that it does not consume a lot of power, because you have to only look at the you have to only perceive those radiation. You don't have to use your own source of radiation. So that is why their life of these sensors is very high. They are just like a camera. So the power requirement for these sensors is very less. Mission life is very high. That is the big advantage. But the thing is that these sensors, which are the passive sensors, they have their limitations, that they can operate only in a certain band of frequency. Like they can work only in the visible spectrum, or they can work in a very narrow range of the microwave spectrum, when Earth emits in the microwave also. So Earth emits in the infrared also. So whatever they are emitting, you have to confine to that. But if you are interested in a certain particular frequency, particular part of the spectrum, which you are interested, where the Earth's radiation is very large, then you have to use a active sensing, or a sensor which can use its own source of radiation to serve a particular purpose. For example, if I'm interested in knowing how much water is there inside a cloud, then I have to use a particular frequency. So whatever frequency is available within the cloud is not of much use, because that amount is very, very less. The magnitude of that radiation is extremely less, so it cannot be detected from a very small size antenna. So for those purposes, several instruments use active sensing. Active sensing gives a lot of other advantages. For example, you can pinpoint a particular frequency for a particular purpose, and generally you can increase, or you can determine the resolution of your sensing also, depending upon the amount of light, and a lot of other special kind of instruments can be built upon that, like the synthetic aperture radar. So in synthetic aperture radar, making a synthetic aperture radar from passive sensing is a slightly difficult and not so successful kind of sensing. People have tried to make a synthetic aperture radiometer also, but it was not so successful. The signal to noise ratio was quite poor. So the thing is that in the active sensing, they can produce a very powerful signal, but it has a cost, that it has that whatever power you are producing from the laser or from the radar or from the microwave, etc., for sending your own signal, it costs you a lot of power. So that is why the mission life of these instruments is slightly lower compared to the passive instruments, because it's like a laser kind of instrument. Suppose you might have used the laser pointer, so you are using your own source of illumination to get the things done. So that is the same principle they use in the active sensing in the satellites. And how satellites see a cloud in different channels. So as I told you in the beginning, that all the visible and infrared channels. This is the picture in the visible channel. And similarly, all the visible infrared, for example, our INSAT 3D satellite, it has 6-channel imager, which is operating in the visible shortwave infrared, middle wave infrared, and then 2 IR channels and 1 water vapor channel. All these things are basically infrared frequencies. And infrared frequencies, they absorb the radiation very quickly. So that is why, because of that, you cannot see more than few meters, or maybe more than a few meters of the cloud in these images. So you don't know what is. Suppose there is one more cloud below this cloud. Suppose just 500 meters below this cloud, there is one more cloud. You will not be able to see that cloud from the infrared satellite. So multi-layer clouds and particularly the warm clouds, it's very difficult to detect. there is a lot of rainfall is taken by the warm clouds. Warm clouds means the clouds which are very near to the ground. So generally, these infrared sensors find it difficult to detect those clouds because the difference between the ground temperature and the upper temperature is very low, and very small difference. And sometimes the signal to noise ratio of these things are not that good. So that is why these kind of sensors, these are called the broadband sensors. They apply a very large wavelength, large band of the wavelength to get this imaging. Otherwise, you will not get this kind of sharp images. So you cannot focus on a particular pinpointed sharp wavelength to get these kind of observations, because otherwise the energy in that particular small narrow band is very, very small. So it affects that signal to noise ratio. So that is one thing. So from the infrared and visible, you get only, you see only the top part of the cloud, only as you can see here. So only you can see the top part of the cloud, nothing below that. But the microwave, microwave, because of its larger wavelength, it can see the clouds to much deeper levels. And that is why the microwave has a distinct advantage in the cloud studies. There are nowadays people are talking about the artificial rains. So before there is a one. So for artificial rains, the people are putting a lot of aerosols and a lot of hygroscopic aerosols. They are injecting hygroscopic aerosols into the clouds, but you cannot put those aerosols into any cloud. The cloud should have sufficient amount of water for that. And how do you know that how much water that cloud has? It is how much water is there. For example, you can see the cloud outside of the cloud from the naked eye, but it is possible that inside the cloud, which you are not able to see, there may be a lot of water in that. So then the people are using a W band, which W band is also a microwave frequency, W band radar. W band radar can penetrate those clouds, can find out exactly how much amount of water is there inside that. Then only they decide to seed that cloud with the hygroscopic aerosols, and that then it becomes beneficial. Even W band radar, W band micro sensors are there in the satellites also. Like in the CloudSat, they have. CloudSat was a satellite which was specially designed to study the clouds, and these double band clouds was able to find out exactly what is the cloud liquid water and what is the water amount inside the cloud. So these are the these are some qualities of microwave satellite. Visible and shortwave infrared also can give you some idea about the what is the water content inside a cloud, because the reflectivity of a cloud increases as the water amount of that cloud increases, and so basically indirectly they can get some idea of how much water might be present inside this cloud. But microwave is actually, nobody can beat microwave for getting that quantitative information about the cloud water amount. Then, as I told you in the very beginning, that there is a three-dimensional cloud seen by the microwave radar. You can see this is not three-dimensional, not cloud, but this is three-dimensional rain, and it is by the TRMM and GPM rain radar. And this is the structure of rain. So it is not cloud. Cloud is much bigger than that, but it is the rainfall when the rainfall is taking place inside the cloud. So you can see that the large chimney clouds here, where the rainfall columns are suddenly occurring at the center of this big convective system. And this information can be very useful, and this serves a purpose that it enhances our understanding of how the cloud formation takes place and what affects the cloud formation, what affects the rainfall formation, etc. These are very important inputs for our understanding. Then the current generation weather satellite, this is the current generation weather satellite, which is very big actually. Let me tell you, it is the weight of the satellite is like a mini truck, and it is huge, and it has many sensors. For example, not only for weather, not only for the meteorology of the Earth, but for the weather of the space. What is space weather? The space weather is basically defined by the solar flares. The sun is emitting a lot of ionized particles and a lot of charged particles, and which ionize our upper atmosphere, which creates a lot of activities in the upper atmosphere. Sometimes it can be very dangerous for the satellites if you are operating on the outside the atmosphere. There are some instruments in the this is a present generation ghost satellite, which is basically American satellite, and India is also trying to build this kind of, or trying to acquire this kind of satellites in future. Probably after 2025 there is a big mission to replace our third generation meteorological satellite with this fourth generation satellites. So they contain lots of space environment in situ suit, extreme ultraviolet and X-ray irradiance sensors. So as I told you in the beginning that we are not having X-ray and ultraviolet sensors right now, but now the future generation or current generation satellites are also having these X-ray sensors. Where they are used, these X-ray sensors, they are used for basically for a space weather. Space weather means they to detect the high gamma ray bursts or high X-ray bursts from the sun and how it can affect the our existing satellite missions. Then there are two instruments which are dedicated to the ultraviolet range of satellites, and they all are basically used for monitoring the solar weather. Then it has this very interesting instrument, geostationary lightning mapper. So basically, this instrument tells you the lightning within the clouds. So it detects the lightning. It is operational all the time. Means it takes every millisecond observations, and it is tuned to a very particular wavelength. It is approximately 700 angstroms, or one very particular frequency it is tuned, because the lightning gives you the signal at that frequency only. So that is why this is a very futuristic instrument on board a geostationary satellite, and it is constantly monitoring the lightning sources, and it is giving a lot of idea for future understanding of our weather and our meteorological systems. Then there is an advanced baseline imager. So this is a very high resolution imaging satellite, which is giving the images of the Earth on different wavelengths. But it is very high resolution. It gives a measurement at every 15 minutes. And there's a magnetometer. So it detects the small changes in the Earth's magnetic field. So this, as you know, that the Earth's magnetic field is very important for deflecting of those ionized particles from the sun. So this is a very advanced kind of system, which is now operational at over the Atlantic region, where basically it is a US satellite. And similarly, a Japanese satellite, Himawari, is also of similar kind of characteristics. So they also have the similar kind of suite of instruments. And India will also have this kind of weather satellite probably by 2025. Then you can see that there are number of important components. We have the satellites from the polar orbiting, as well as the geostationary orbiting satellites. There are a huge number of satellites, and there is a system. There is a global observation system, which is depending upon both geostationary and polar orbiting satellites. It collects the data from many platforms, including the buoys, ocean buoys, etc. So apart from observing the weather, these satellites also play a very major role in communication. So whenever there is a data is collected from a weather station, it is transmitted through these satellites. So inside 3D, not only does a observation of the Earth, it also collects a lot of data from ground-based instruments and provides this data to a central unit, where this data is finally gets disseminated to the GTS, the Global Time Telecommunication Service, and where it goes within seconds, it gets available to all the centers of the world, and then they use this data into the numerical models, and then you get the weather forecasting. So this is not just one satellite; it is a system of satellites which is operational, and they provide very timely observations to within fraction of seconds, or within a minute or 2 minutes. These observations gets available to the weather centers worldwide, and and then they assimilate. And not only they assimilate the observations, they actually filter these observations also, because sometimes some observations might be faulty, because everything, even satellite sensors have an age. They get aging effect. They get sometimes they get defected also. Sometimes, so it means a agency or any center or any system that is using these observations also has to be very careful that what is the quality of these observations. So data assimilation of these data into the models itself is a very dedicated, very involved science, and there are a lot of separate centers for that, which are working on those kind of things, that how to filter, how to check the quality of these observations, and how to get maximum information from these satellite measurements, so that they can be useful for the weather forecasting community. Then there is you can see there is a complete system of weather satellites, which contains many geostationary satellites. You can see all the satellites on this ring are basically the geostationary satellites, and there are a number of meteorological, number of geosynchronous polar satellites. Like this is the, you can see that I mentioned about this geosynchronous orbit. So Canada, Russia, these people are using these kind of geosynchronous orbits for repeated coverage over their area. Then there are a lot of other satellites dedicated to the operational services as well as the research services. For example, polar orbiting satellites. There are satellites for measurements of the winds. There are TRIM and the GPM satellites. They are dedicated for the measurements of the rainfall and so many things. Ocean surface winds, ocean surface temperature, sea surface temperature. There are n number of variables, aerosols, air quality, and then fog, vegetation. So many parameters are there by which these satellites are making measurements of. India has its own series of satellites. Now we have, the inside VHR. It's starting from 1990. So India is active in the geostationary satellite business for a very long time. And then INSAT 3D was there in 2013. INSAT 3D-R was 2016. So these are the operational satellites of India. INSAT 3D-R was again in 2016, and then GISAT was launched in 2020 or 2021. I really don't remember, but it is launched recently. And all these satellites are actually providing very valuable measurements of in and around Indian region. And India also has a very decent legacy of polar orbiting and low Earth orbiting satellites. The notable of them is basically OceanSat-3, GCOM, Megatropic satellite, Salal, OceanSat-2. One of the very big achievement of Indian satellites is basically the development of a scatterometer and ocean color monitor. They can provide a lot of value, a lot of information about the oceans, like ocean color and ocean surface winds, ocean nutrients, turbidity, etc. So many other things like vegetation, oceanic vegetation, and so many other valuable parameters which are used by different models and different things. They are the different satellites by comparison. Nowadays, the satellite which I just showed you, it weighs just like a mini truck actually. So which is having a weight of approximately more than 3,000 kilograms. And you start from those satellites, and you have a very small satellite, Earth observation CubeSats, which is having a weight of hardly 9 kilograms. And there are many such satellites, many such satellites which provide you a very specific measurements. Like they will provide you the measurement of rainfall. That's all. And then there are many hundreds of such satellites. So you don't get the problem of coverage. So if one satellite passes from the horizon, immediately there is another satellite which comes to replace that, and you never get a shortage of those observations. And continuously this set of observations from the polar orbit, they provide repeated coverage because there are many satellites are there in the orbit. And there is a problem that how many satellites are there? Till now, actually 11,000, more than 11,000 satellites has been launched, including all type of satellites. So 11,000 satellites has been launched. And active satellites are approximately more than 3,000. Out of that, there are 900 Earth observation satellites and 60 meteorological satellites, which are currently active. So meteorological satellites is very small number compared to the total satellites. There are a lot of other communication satellites, Earth observation satellites, so many kind of other satellites are there. So even though there are meteorological satellites are not many, but they play a extremely vital role in our day-to-day activities. So this number is keep on going up and up and up. So there are many satellites which are in the pipeline yet. So this is I'll briefly tell you what is about some INSAT 3D. So INSAT 3D was the first satellite which had a sounder, and sounder means a instrument which can give you the idea of the vertical profiles of the temperature and humidity and ozone also. This is a very important development, and just on 26th July, the INSAT 3D completed 10 years in the orbit. So it is constantly providing services for 10 years, and after American satellites, this is the only satellite in the world which can provide you the vertical profiles of humidity and temperature from a sounder instrument. So this was a unique feature of the Indian satellite. So basically, you can see that the multispectral imaging. So multispectral imaging means what you can see in one frequency is something very different what you can see in other frequency. For example, to us humans, this flower looks like this. This flower looks like this yellow flower. But to a honeybee, this flower looks like this. The same flower looks like this to a honeybee. So just by spectral difference, this honeybee can get a lot of information about how much juice or how much nectar is there inside that flower. So what you see, what you and I see in a flower, and what a bee see in a flower is quite different thing. So it gets information of its own purpose. So similarly, we can get information for our own purpose from different channels. So why we require different channels? So what we get from visible channel, what we get from the infrared in the shortwave infrared channel is quite different. Can you see this very, very bright bands here? And the same thing looks very dark in the sphere. But some other parts look very bright in both of them. So there is for example, you see this line. This line looks bright here also. But this looks very bright in the visible channel, but this looks very, very dark in the shortwave infrared channel. These dark regions are because the ice particles absorb the shortwave radiation very quickly. And that is why this darkness, if you see the difference between this and this, you can see that these are the regions where there is a lot of ice particles, ice nucleation there's a lot of ice nucleation here. And that is why these regions are having a very high chance of raining immediately. So this is called synoptic weather forecasting, where you can see that image, see the image difference, and then you can immediately get a conclusion and you can make a warning that okay, where there is a big chance of raining. So based upon that, there are algorithms people have made where they can determine using these two bands that where are the chances of immediate rain. Similarly, middle wave infrared, it has a very high importance in detection of the fog. Generally, it is difficult to detect fog in the night time with this frequency or this frequency or this frequency, because first of all, in the night time, these two channels are not available. This MIR will give you some idea of the fog, that what is the fog. This is very sensitive to the low level temperature, and it can differentiate between the ground temperature and the fog temperature. And that is why this is used for detection of the fog. This is the water vapor channel. This provides us the surface level winds at upper level for 6-7 kilometer height. These two channels are used to determine sea surface temperature because they are highly sensitive to the temperature of the surface. So these two channels are used for not only cloud top temperature, they can be used for the land surface temperature, they can be used for the sea surface temperature, and they are highly sensitive. And why there are two channels? Because one channel is not sufficient, because this total emission and whatever total thermal emission is coming, it is coming a combination of the water vapor and the surface. So there is two components are involved in that. So water vapor plus this thing. So whatever is emitted from the ground, it is absorbed by the water vapor. So you don't know that how much is coming from the ground and how much is absorbed by the water vapor. So there is a equation with two unknowns. So we require two equations for that. So for that there are two channels. So one channel is slightly more sensitive to the water vapor than other channels. So that is why these two channels are put in the algorithm, and they can be useful to cancel out the effect of the water vapor. And that is why they are very much useful for the sea surface temperature. This is the advantage of geostationary, because in the geostationary we can track one cloud continuously without motion of the earth. So if this is not geostationary, then this map etc. will be also moving. So because the Earth is moving, so it is a big advantage of keeping the Earth fixed, so that we can monitor big hazardous systems like tropical cyclones, heavy rainfall systems, etc., etc. Like the winds. Without a fixed platform, we cannot measure the winds also, because in the winds we have to measure the movement of the clouds, and if whole platform is moving, then we cannot determine the motion of the cloud, because then this equation becomes very complicated. So we have to fix the frames, and then from geostationary, and then we can. And you know, these winds are the only source of the upper level winds in the presence of clouds. Even those meteors, etc., they like ADM and laser-based systems, they can't detect the winds in this kind of situation. They provide, this is a very valuable source of information of the upper level winds, and extremely valuable input to the numerical weather forecast models. These are the different measurements which you get from satellites, like inside satellite, outgoing long wave radiation, upper tropospheric humidity, solar radiation, you know, very much useful for the solar energy, sea surface temperature, water vapor winds, winds and upper atmosphere winds, qualitative rainfall, quantitative rainfall. You know, quantitative rainfall means it is not just that it is raining. We get quantitatively how much it is raining, 5 millimeter or 10 millimeter or 20 millimeter. So these algorithms have been developed over the period of time to determine exact quantitative assessment of the water. Then fog, snow, aerosols, etc. I think 40 products are determined from InSat 3D, imager and sounder together. There are a lot of products which are used for cyclones, tropical cyclones, enhancement. What is the intensity of the tropical cyclone? Where the cloud mass is more concentrated? What is the movement of the tropical cyclone? There are a lot of tropical cyclone related products which are coming from geostationary satellites. Then there are the active sensors, lidars. You know, they sense the entire column of the atmosphere in the clear sky area. So when there is a cloud, then these things they don't use, they can't give measurement there, because they are tracking aerosols and water vapors. Similarly, there are measurements from temperature from the microwave, which is the temperature and humidity profiles. There are spectrometer winds, sea level from the microwave, because sea level, you know, it is like a small beam which goes exactly vertically downwards, and it comes back. So depending upon the shape of the return beam and time of the return beam, they can find out what is the level of the sea. And because sea is not constant, there is a constantly waves are moving up, so it has to be averaged for a very long time, and then they get exactly this measurement to the accuracy of few millimeters. And these are the other measurements from microwave satellites. Yeah, this is one instrument. This is my last slide. You know, there are GPS satellites, and everybody in our today's time is using GPS satellites. We are using all our mapping. Your taxi driver comes and he tracks down your location, your delivery parcel. Everything is using this GPS satellite system. You know, this all the mapping and all this your Uber, Ola. Everybody is nowadays. It is very difficult to imagine the world without this service. This is a constantly professional service, and then it is not meant for basically for meteorological purpose, but meteorological people are using it for great advantage. You know, there are a lot of meteorological satellites, and ultimately these sensors, you know, this GPS satellite is sending these measurements to the low Earth orbiting is sending these measurements to the GPS satellite. And you know, these radio signals, they have a time tag, and they should reach to the GPS satellite or to some other satellite at a particular time. So if there is a delay of this there is a 0.00001 second, then you can determine what is the path of this beam, what is the curvature along this path. And this curvature, you know, is a function of the temperature of that layer. So it means the delay of these signals from the GPS satellites can be used to determine the temperature profile, vertical temperature structure, where it is more hot, whether it's temperature, where the humidity is more, where this thing is, and it can be done very, very precisely. So this is, even though this was not used for meteorological purpose initially, but this gives us extremely accurate information of the vertical profile of the atmosphere. And this particular observation has the highest impact, one of the very highest impact per observation on the numerical weather prediction. It is because vertical structure of the atmosphere is this is what decides whether your weather will become highly convective or whether it will become unstable, whether it will become very violent, etc. All these things depend upon how your weather is stratified, how your atmosphere is vertically stratified in terms of temperature and humidity. So this is another thing, the GPS reflectometry. So this I'll tell you. This is the same thing, but the GPS signal. Actually, GPS signal comes from the satellites to the ocean, and then it gets reflected to the another satellite. And based upon the reflected signal, the strength of the reflected signal, time delay, etc., you can determine a lot of properties of the ocean surface. For example, you can determine what is the winds at the ocean surface, and this is one of the quite accurate instrument. But it was launched in, I think, 3-4 years back, but I really don't know. There is it is still under research. So this is all my talk. Thank you very much. My time is over.